Sometimes that's all it
MIT
is.
is dead and MIT guest is okay.
Yeah, I got it too.
Okay.
So has there been any speculation as to how long until we're going to see Raspberry Pi 4s that have got the USB-C issue fixed? Are there any predictions on that front? Has anyone heard anything?
Well, wasn't there a class of purchasers that they've already taken care of? Wasn't, if you bought it from a certain like element 14 or something like that, they would take care of it?
Maybe.
I thought there was some class of early adopters or something.
Actually, I'm connected to MIT, not MIT guest.
Ah.
If DeLacy comes, I'll ask him because he was researching it. I could have sworn there was some sort of a priority system.
My impression was that they were not going to fix it, period. They were just going to say,
I've got an 18
well,
dot.
use our power supply or use
Yeah, see, you can see down the bottom here.
non-marked cable.
Yeah, you got an 18 dot. Yep.
Apparently,
The super low end and the super high end work.
no. The low end generally work. The higher end are quite a bit less likely to work.
Oh, all right.
Basically, they left off a critical resistor, at which point the markings don't work right and everything fails.
Yeah.
Cheap cables work. It's the nice cables that don't work.
Yes. Both the cable and the device are supposed to have appropriately sized resistors. Raspberry Pi, they left off one. So if they also left it off in the cable, everything's fine. If there's one on the cable where it is supposed to be, then Raspberry Pi 4 will look like the wrong sort of device, and a smart power supply will not power it. A dumber power supply, which simply says, oh, it's something that takes 5 volts, all I do is provide 5 volts, and nothing else, then it will actually power it.
Yeah. So that's going to have to go in my book, Trivial Defeat for Complex Systems. So about 2 years ago, somebody wrote a how-to on how to defeat one of those really nice bicycle locks with
Kryptonite?
the kryptonite.
Yeah.
How to defeat a kryptonite lock with a cap from a ballpoint pen. And it turns out that's just the right tensile strength of plastic to be able to stick it in there.
And then rotate it
it'll
so
feel,
there's
it'll feel the
Mark.
Yeah, so it's not too
6:55
soft, it's not
and
too
30
hard,
seconds
but you stick that
p.m.
little thing that hangs
Wednesday,
over
October
your
16th, 2019.
Wiggle
Blue
it
Meeting.
enough and it's like, hey, kryptonite lock. So I don't know what kryptonite has done to solve that problem, but I'd be brokenhearted if someone. I mean, it's bad enough somebody steals your bike,
Right.
but to steal it with a 5-cent piece of plastic,
Right, yeah.
that's the real indignity right there.
Yeah, if somebody came with bolt cutters and did that.
This guy at least put some skin in
Some
it.
effort, yeah.
He would have spent $25.
If you want to know how bad the situation is, there's a YouTube channel, The Lockpicking Lawyer.
Oh.
Don't watch it. You don't want to know how easy it is. Just don't. I mean, he does find locks that are really, really good.
Yeah,
And then there are others that just aren't.
yeah.
And it's not obvious from the heft or the manufacturer or anything else.
Yeah. There was another how-to on, and I don't know if this is still true, but the way that if you're playing pinball or something like that, and you're throwing quarters in there, the way it recognizes that a quarter is going in and like breaks a beam or something like that. And this guy had a how-to on. You just hold a lighter up to it, and it somehow flashes it and thinks that a quarter went through. And this guy was showing, just playing game after game after game, and he just flashes lighter in front of the little slot that the quarter goes in. And it's like, so they couldn't have figured this out, hundreds of hours.
Well,
at really
they
expensive
probably did. It's just, again, it was just the right level of light,
Yep. And the right,
and
Spectrum.
and probably also the right timing.
yeah.
How does it know it's a quarter and not a dime?
Right, and maybe it,
It has like a diameter of the beam.
yeah, or maybe it's falling at a particular
Are kind
rate
of
because
holding
it's
off,
not-
John, on
Yeah. But still, you know.
The way the front,
I mean, that's pretty much what Newton. In a vacuum. I mean, it's not a vacuum.
The distance is such that the air wouldn't.
I know. I'm kidding.
It must be like how long the beam is interrupted.
It is
Yes,
to measure
yes,
the-
yes. That
Yeah.
could be, but you could have it.
It is to measure the conductivity in the plate.
But then wind would change the,
Right. Do we actually think too complex? It might be much simpler.
Yeah. Yes, it could simply be, it's basically got a little track, and the beam is high enough up that the quarter will go under the
right, right.
or a dime will go
No,
under
under the beam,
quarter will
right,
go
yeah, right.
there. On the other hand, then you've got the problem of what happens if someone sticks a Susan B. Anthony dollar in there.
It jams.
Probably.
I mean, usually you have the problem of people trying to scam this thing, not give them more money.
Well, I mean, if you wanted to buy several beans at once,
So we have vending machines at work now that says guarantee refund if like they have some way of sensing that the candy actually dropped.
Oh, really?
So if it doesn't drop, it gives your money back.
well, all you need is you need some sensors
At the
On
bottom,
the
yeah.
bounce. But did the right thing drop?
I don't know about that. I don't know about that. But it says that if your product didn't drop, then you get your money back. And that did happen. Then get jammed, and then I got ordered out.
Huh.
Okay.
Now, did the guy that came in after you, did he get like 2 bags of chips from the, because it's on the,
Yeah,
it's on the
I don't
swirly
know.
things,
Yeah,
right?
I don't know.
Well, you could try that. Stick your money back in and see if
Yeah,
it
let's
takes.
see if it does one more spin.
With the old machine, I tried that.
What are you doing after?
I really wanted like a Mars bar or something, and so it didn't come. I said, okay, maybe I put more money, it too will drop. And then both jammed, and I didn't get anything.
I'm wondering on fixed.
You know, every time I have that happen, I just grab the top of the machine and like push it. I push it back once and let it drop, and the thing comes right down.
Or the entire machine falls over on you and you end up.
I don't push it that far back. I put my hand at the top.
or if
I
the
push
machine
it back
just
about
says
like
tilt,
maybe 4 or 5 inches, and then I just let go and let it drop. I don't pull it toward me.
Yeah, but depending upon where the mass distribution of the machine, if it's heavier at the front, pushing it back could actually cause it to fall forward. That's not
I don't push
that
it very
likely,
far.
but- As I say, I discovered that apparently one or some number of people managed to put together basically a UEFI chaining firmware for the Raspberry Pi 3. So you can get something that looks very, very, very suspiciously like a PC BIOS on a Raspberry Pi 3. And if you simply have an ARM red image,
Okay.
you can actually install from that for a
gonna go
number
get
of
some
Linux
potato chips.
distributions.
Yeah.
Okay. Just confirm that live streaming is functioning properly. And so far,
I'm doing research though.
stream is healthy. Good.
Apparently there's an experimental, well, I guess I would call it there's an experimental install of Zen for the Raspberry Pi 4. There's not one for the Raspberry Pi 3.
So is your Raspberry Pi working, or do you need it?
I don't have one yet. I am waiting
You
for,
waited.
yeah. since there's a little bit of experimentation I would like to do.
Are the 4 gig versions back in stock?
I think they are.
I looked in Micro Center a while ago and it was on. So that's the one I want.
I was looking at them like almost about the time of the last meeting, and Micro Center listed them as in stock.
Oh.
I thought, as I say, is that at this point they've probably been out long enough that we should start actually seeing real numbers of them. The question is, how long is it going to take to fix? Oh, we left off one critical resistor.
Rumors of an 8 gig version too.
Well, it sounds like the rumors are. It sounds like they think that there may be one sort of being thought about, but that's probably not going to happen until they can get 8 gig memory chips cheap,
Mm-hmm.
and that could take a while. Let's put it mildly.
I've been buying legacy Jetsons because NVIDIA's dropped the price on everything but the state-of-the-art Jetson. But more importantly, somebody's got a Debian for Jetson port out there that's really nice. It's got a much more recent kernel on it than Linux for Tegra, which is, of course,
Ancient, yeah, yeah.
Okay, so and the Jetson Nano is $99. It isn't, a performant, single board computer, but hey, $99. If you want to learn CUDA.
Hey, Bill.
Hello.
Very stylish. Where are you coming from? Right. A soccer match?
Is this you?
Yeah. That's the key to Arsenal.
Oh, wow. I got my work to do.
That's it, the revolution.
Who have achieved my victory condition for the year.
Yeah, that's right.
They have a playoff game later in October than the Red Sox.
Yep.
Some years that's easier than others. So, you have a upcoming deadline?
Yeah, November 11th. We got time.
Does that mean you got through the
Well, I'm going to have to
early
read
phase?
So I had submitted a year ago. I didn't realize it was every 6 months. But let me go back and find, because when you made that reference, I said, well, I got to go back and read the instructions.
Yeah, you do that.
Yeah, I might be missing a couple things. But I don't know. We submitted V1 and V2. This is V4, right? So I don't know what we did for V3, but I'll go back and look.
Actually, for the heck of it, does anyone know why there are a number of cell phones out there that you can get with 6 gigs of memory, and that's just kind of, why do you get 6 gigs of memory on a cell phone? Yes, it's more than 4, but the thing is, it's not a power of 2, which means it's unlikely to be one chip. And
They might be using 3 cheap chips.
yeah,
The answer on the Trash 80 for why it maxed out at 48K was that it didn't map out the ROM. So the ROM was in address space. Which was not new to me because the PDP-8 that was available to high schoolers had 32K total in 2 separate banks that were 16K addressable. Bank 0 had 10K of RAM and 6K of ROM. And bank 1 had a full 16K of RAM. By RAM, I mean, donuts threaded on wire. And
It is randomly.
and you could partition it to support 3 terminals. So you normally partitioned it to have 3 interpreters, 1 in the 10K remainder and 2 8K partitions in the second bank, because nothing could span banks. One day I got in to the lab before the graduate assistant and rebooted it to split 5, 5, 16. And it's amazing how long it took anyone to notice that the program that fit fine yesterday didn't fit today. This was on a true interpreter where it costs you memory to write good comments. And the graduate assistant had been quite clear that he was going to be grading on comments. But I had a lot of comments and a lot of error checking. So it wouldn't fit in 8K when it was tight in 10K. So I got 16K. First several people fit in 5K, no problems. I don't think they had error checking or comments.
You got an A at that expense.
Heck yeah. And he was a little startled that one of the high school kids had watched him closely enough on when he booted it to know how to boot it and repartition it.
Yeah, I mean, so these days, so you have the MMIO hole between 3 gig and 4 gig. So every PC address between 3 gigabytes and 4 gigabytes is mapped to I/O.
Yep.
And then in our hardware, we have all kinds of gyrations to not lose the RAM that's mapped to those addresses. So there's this thing where you take that 1 gig of RAM that would normally be a RAM address and hoist it above, so that if you have 4 gigs of RAM, what would normally be in that 3 to 4 gig is now in 4 to 5 gig address. So
I think we ought to go back to core.
Core has the great advantage that you turn it on,
Yeah.
that you don't have to have special Linux drivers for suspend to work with Core.
Yes.
What you do need is special drivers to declassify memory after you turn it off.
The more extended shutdown procedure.
The Burger King point of sale I worked on
Thermite works.
was a 4K PDP-8. And it was a really nice machine. It was all written in assembler. And when we would load a new version up there, we had a scratch pad. And what the first thing we'd load in the scratch pad was the comms routine. And then we would go and plug the address of the comms routine in. So the comms routine then would load the rest of the program. And the comms routine, so every release, the comms routine and the scratch pad switched.
So it looks like you've got a cell phone which is pretending to be a dumb phone there.
That is a dumb phone.
No, sorry.
This is not a phone.
Well,
This is not a phone.
the thing that is still on that thing, somehow I'm really doubtful it's actually a dumb phone. You know what? I suspect it's probably got more than 128K of memory.
I suspect it has
In fact-
a lot more memory than it needs.
Yes. Yes. In fact, it might even run Android It's just they've hidden everything to make it pretend to be a dumb phone.
I don't know. It's even dumber than my last dumb phone.
Or, well, it pretends to be dumber than your last dumb phone.
What do you have, Bill? Let's see.
Oh, it's called a Cool Pad.
Oh,
Definitely aimed at aging boomers. Yeah, my previous definitely was a feature phone on the inside as well as the outside. What was becoming problematic is they started unplugging 3G nodes every other one.
I have to say, the first cell phone I got was an actual sort of dumb phone because
My first cell phone was definitely dumb. It came in a bag this big, took the same battery as a video recorder,
yeah.
Had one cord for cigar lighter and another cord for the mag mount on the roof of the car. And a full 3 watts out. with the omnidirectional mag mount, which got really good service.
Yeah.
What plan were you on? Night Owl or something?
I think originally back then,
Yeah,
which meant that pay for business calls, but they were business.
yeah, the plan.
I had that cell phone for a little while, and then after that, for quite a few years, I had a Treo 680 because, you know what? Once you've got the PDA, it eats your memory of contact information. You just lose that. And it's, you know what? It's Palmas, it's limited, but it's actually quite usable for what it does. It's very usable. Even though it's limited.
Palm? You think Palm?
Yes.
Yeah.
But because I found an appropriate program, I managed to find something which will, they're calling it DAVX, which is basically an open source thing to talk to sort of, I think, CalDAV and a few of these other similar sorts of protocols. And the thing is that there is, in fact, a program to talk those protocols for Linux, so the entire thing is open source.
okay, Shankar,
Yeah.
you can come on up if you want.
There's a presentation.
Either that or Elliot can come on up.
Talk about Symbian. Where's Symbian? Is Symbian a Unix? No.
I haven't heard Symbian in a long, long time.
Does the new Nokia still use it or no?
You didn't even hear the ah as they got bought out by Microsoft.
Yeah.
You doing?
Or actually, first they stuck there. They replaced the CEO with the
That's right.
Microsoft employee.
That was,
Then
that was my disaster with Mamo.
Oh, right. That's right.
Yeah, perfect.
Okay. So, Joe, you want to do the introduction for the camper?
Okay. Okay. Okay, tonight we're going to do from design to production on silicon. And we've got Shankar, and I've never been able to pronounce your last name.
Viswanathan.
Okay, that's good.
Everybody has trouble, it's fine.
Yeah, I know. And I've known you for 20 years. So,
That's V's for nothing?
Is the general rule emphasis on the second syllable?
Yes. So the funniest story was when I first went to get my driver's license. This was in Indiana.
They required
The lady there like tried very hard. I could see her like trying to pronounce my name like 8 times in her head. She's like, "I'm sorry. I'm just gonna give you this number. Just show up when the number comes." Like, okay. So I would rather not butcher your name. I'm like, okay. All right, let's get started. Okay, so for those who don't know me, I work at AMD, and I do hardware design mostly on sort of the logic and performance aspects of it. Of late, I've been working on AMD has a group called the Semi-Custom Group, where we make custom silicon for specific customers. So examples would be the chips that we used for PlayStation 4, Xbox One, and now we're working on the next generation of those consoles. But anyway, so this talk is not specific to AMD. I use a couple of examples for AMD chips.
In terms of shipping volumes, right, when you're talking about like a custom chip, aren't there like way more console chips that are shipped than any like one particular desktop processor over the lifetime?
That is very true.
So it is kind of like you the way it sounds like it's a sort of some boutique thing, but in reality, right, it's actually a bigger number of shipping.
Oh, by volume,
right?
it's our highest volume product, right? So I don't know the latest numbers, but like I believe just if you combine the chips for Xbox One and PS4, we are over 100 million.
Wow.
And you know, to get like a server chip to get into 100 million, it'll take us 10 years to do that, right? And or actually even more. This is over about 5 years. We've sold about 100 million is the estimate. But yes. So I mean, and sort of the genesis of this talk was like I've been asked several times. It's like, oh, I understand how software development works. I have no idea what you do when you design hardware. Like, what are the steps? So this is meant to be like a high-level overview of the whole hardware design process, and then how we get chips back, how we test them, and then how we eventually get it into production and into the market. So anyway, so that's the sort of the overview. I'm not an expert at most of these things. There's a few things that I know really well. The rest I'm kind of lost, but I'll try my best to answer any questions. And feel free to interrupt me and ask questions anytime. Don't want this to be a monologue. So here's kind of the outline. Go through sort of the initial design process. So this is all the way from concept to, we have the design completed, and then then we go on to initial manufacturing and test, and then eventually, volume production. So let's go through the design flow, right? So this is kind of the high level steps involved in the design. So the blocks on the left here are the thing that goes into the design. And then the stuff on the right is to make sure that stuff on the left is correct, right? So there's all these checks that happen at every stage, and there's feedback back and forth. Typically, once you define the product, it's we don't go back and change it unless there's we came up with some concept, we started implementing it, and then halfway through we decided, oops, this is too much. We try to bite off more we can chew, and so we go back and change the product definition. But that's generally rare. We have very experienced architects doing the product definition stuff, and it's usually have a good idea of what we can build, right? So anyway, so it starts with the product definition, and we kind of go through all these steps in more detail. And to know whether high-level concept, if that's good or not, we do these high-level model simulations that kind of say, okay, at a first order, this design looks okay to meet what we need for the market. Then the next step is the actual meat of the logical design. So this is typically done in hardware description language like Verilog or VHDL, and you map out the full design. And then on the right there is the design verification, which basically checks that logically what you design is meeting the spec from a functional standpoint. And then the last stage is the physical design, where we take this logical representation of the chip and convert it into actual transistors and layout and how the whole thing is connected. So the final wiring diagram. And then there's a bunch of checks that happen that wiring and everything, again, matches what we intended to build and that it's internally self-consistent. So anyway, we'll go through all that steps. We'll start with the sort of the first box here, which is the product definition, and then the high-level simulation. So for product definition, you know, what do we talk about, right? So the first decision that has to be made is what technology node are we going into, and by that I mean, okay, is this going to be a 14 nanometers, 10 nanometers, 7 nanometers, 5 nanometers? What is a technology available? And then for this particular product, what is the best fit, right? So when you talk about high performance microprocessors, you typically want to be at that leading edge. You get benefits in terms of performance and power, right? But those also tend to be expensive and less proven, as in you could have a lot of manufacturing defects because the technology is not completely mature yet. So if you want to be
Is there interaction with external customers at this stage, or is it really just internal discussion?
This is mostly internal discussion. In our case, like the group that I work in, like if we are going to tailor it to a particular customer, they might have some input into it, right? It's based on their business too, like how risk tolerant are they, right? You might want to, for their business needs, they might want, I just want a solid, proven thing. Even if it's one generation behind, I want guarantee that this thing will work, right? Because there have been cases where the design is ready, but the process is not, right? So you've customized your design to go into, let's say, I don't want to beat on Intel, but AMD had this issue a while ago. So for 32 nanometer product, the design was ready, technology was not ready. So basically the design had to sit till the process guys got the process improved to a point where like, okay, now we think our yields are going to be reasonable, right? And you don't get one die out of an entire wafer, right?
Wait, so this is a sort of on this sort of Intel tick-tock model, right? When they go to the next generation of process, how much redesign is it?
In the historically, historically Intel's tick-tock model is where you on a known process you do architecture innovation,
yeah,
right? You redesign your circuit, you come up with new ideas, right? And then I forget which one is the tick and the tock, right? But in the next one, you take the same design, you virtually don't change it, right? Logically, right? And you just port that into a new process, right? So from a logical standpoint, you have very little risk because you know the design
sort of three phases. Where does then the redesign is on the physical part? I'm just trying to understand, like, if the process isn't ready, it's not practical to just use a larger process if the design is waiting for it. Is that right?
Yes, because there's a whole bunch of work that you'll have to redo, right? Maybe I'll explain that when we get to that, right? But it's not that easy, right? And sometimes you might have to say, well, I have to abandon this node entirely and I have to go back and redo the whole design in this new process, right? Things happen, or like for companies that are fabless, right? They don't have their own fabrication. You might have to go to one vendor and then they find, oops, this vendor is not delivering what they promised, and now I need to go target somebody else, right? And then there's all the collateral that you have to get from the other guy, and then now you have to customize your design for that guy, right? It's getting easier now, but there's still a lot of stuff that has to get redone.
Does AMD has its own fab, right?
Not anymore. No, Global Foundries. So we spun off, AMD spun off our fabs as Global Foundries. This is, I don't know, almost a decade ago now. But you know, AMD is open to go to other, like we go to TSMC for some of our products. So that's the node, and that's a very important decision because a lot rides on that decision. So you want to get that right. And then next is like high-level features, like okay, if it's you're talking about a processor, how many cores do I want? You know, how much memory do I want to support? Do I want to include some graphics? Do I want to include, you know, other blocks? You know, PCIe lanes. You know, do I want to support USB or Wi-Fi or any of these things? So depending on the market, you want to decide high level what this is going to be. And that kind of goes back into the constraints provided by the technology node, right? So you want to say, sure, I could build a 64-core chip in a 14-nanometer process, right? But that chip will be this big, right? And I can't manufacture it, or I can't manufacture it in reasonable, you know, profitably. So some of that will be constrained by what you can actually physically manufacture. The next constraint will be power, and that seems kind of obvious, right? So if you're a server product, you have a certain power envelope. If you have a laptop or a mobile phone chip, you know, you're in a completely different power regimen, right? Region. So then you're again, all of this will have to be factored by the power that you have, and kind of that goes hand in hand with performance, right? So typically, if you burn more power, you can get more performance. So those two kind of go together. But then there are some other things you can do for performance, which are power, you know, less power hungry. But you might have to pay for that in chip area. So I can make it more power efficient, but that makes the chip become bigger. That again goes back to what node I'm in. So all these are, even though they're separate things, they're all kind of interrelated, and you have to look at this as a multi-dimensional problem, and you're trying to find that optimal point that satisfies these things as well as whatever market that you are trying to target in the time frame that you want to target. Typically, if you want to start from complete scratch, which nobody does anymore, but if you say I'm going to throw away everything I have, and I'm going to start today and design a processor for a laptop, your design cycle is going to be about 3 years. Just the design, right? And then you have your manufacturing test, blah, blah, blah. By the time this product hits the shelf, will be anywhere between 4 to 5 years. So if I'm thinking about the features today, I need to figure out what somebody would need 5 years from now, right? And that was fine when you know, we could rely upon Moore's law doubling every 2 years, and you know, people were buying things every 3 years. They were upgrading, so you kind of knew what your market was going to be like. It's much harder now, right? The cycles are compressed, so nobody redesigns everything from scratch anymore. So you kind of decide which things you're weakest on, and you focus on that, and try to leverage the other strengths as best as you can. So
in terms of future proofing, like things that only exist on paper, you have to just like PCI 5 or HBM 3, whatever it is, right? There's no chips for this, right?
No.
Like there's no PCI 5, 6, whatever device, right? There's no memory controller. Like how?
Exactly that. Those are the challenges, right? So you have to know that if this product has to come out a year and a half from now, right? Should I target HBM2 or should I target HBM3? And you go talk to those vendors, right? You go talk to memory vendors or other PCIe suppliers, like, are you going to have any? So one way you can solve that is by saying, okay, we'll be backward compatible, so we'll be both PCIe 4 and 5.
Yeah, but it costs money.
Costs money, right? But you're protected that if the PCIe 5 people don't get their stuff together, you know, because some of these are standards bodies, and you know how standard bodies work. To hedge your bet, you have to design for both, right? And then that way you're future proofed a little bit. But other times you have to make a call and say, okay, do I go with the proven but slow, or do I go with the cutting edge and then take my chances that the ecosystem will be there, right? Yes, there's a lot of
It's like
constraints.
gambling. You're basically gambling.
Oh,
Three
absolutely.
casinos, or 5 casinos
Absolutely.
at the same time.
Absolutely. Like I said, the odds are better now than they were before because you're designing for 5 years ahead. You have no idea what's going to happen in 5 years, right? So you are in like 2003. You're trying to design a laptop chip, and then you don't know that the number one thing everybody does on their laptop is going to be Facebook and YouTube, right? How do you design for that? So at least now the cycles are, it's more like a 2-year cycle, right? From starting to when product will come out. So you have a slightly better idea, but there's still a lot of tough bets that you have to make, right? And the cost of being wrong is enormous, both in terms of physical cost and time to market and lost market share and all that, right?
You design the masks, manufacture the masks for the foundry?
No. So the typical. So AMD, if you're asking about AMD, we don't manufacture them ourselves. So we send the design off to a third party.
And they make the masks.
They make the masks. Yes. So the last thing is, like I said, chip area, and that's directly proportional to cost. So here's an example of what like a high-level product sheet would look like. I don't want to go through details, but this is something this is the final product definition slide after the product came out. But you can imagine there's something similar that happens up front, right? We say, okay, these are the things that are important to us. This is what the market wants, and these are the things that we can do in this product timeline, right? So there's an example of the latest Epic server. We decided, okay, we should have 64 cores, each of them 2 threads, and we can't do a monolithic die, so we have to break it down into all these chiplets, right? And then we'll have the common sort of the I/O stuff in the middle, and that handles all the DRAM and all that, right? PCIe, all that stuff we put over there.
Is that all AMD IP, or do you license like memory?
Most of it is AMD IP. There might be a few things that we license from outside. So, for example, the secure processor, that's an ARM core in there. So that we license from ARM. There's few other cases, like bits and pieces that we license from other companies.
So that's a trust zone. You license.
That's trust
zone.
zone. Yeah.
And that's the only ARM licensing,
I believe so, right? I believe that's the only ARM thing. So there are certain analog blocks that we, again, license from other companies because those are completely tied to the particular manufacturing process. This, again, allows us to not have to design to a particular process, to a particular vendor. That way, if we decide, we want to take this chip from Global Foundries to TSMC or vice versa, then we can simply swap that block for something equivalent that vendor has for the other guy, right? So there's some advantages in doing that. So it's the analog blocks that are typically most dependent on the technology node, right, and the vendor. So those are the things that we, as a strategic thing, AMD has decided to license rather than do ourselves, right?
I'm kind of curious about that last line on the left. Is that saying that we're soon to be seeing memory chips are 4 terabytes for each DIMM? How many years out is that?
No, so this is this line here.
Yeah.
That's just saying how much we support, right? It's up to what DIMMs you can get, how many of those you can put down on the motherboard without breaking all the signal integrity stuff. So there's a lot of other things, but from a chip standpoint, we can support this, right? And particularly when you're talking about a NUMA config where you stamp multiple of these on the motherboard, then it matters, right? Because then you can have a few DIMMs associated with each of these sockets, and then combined it can be terabytes, right?
Yeah.
So-
For example, one thing I was actually sort of looking at this for curiosity's sake. I was seeing a motherboard that was reputedly supported a terabyte of memory, but the largest DIMM they actually had available out there was 64 gigs, at which point with 8 slots, you can't actually reach that because there aren't any DIMMs large enough. It's also interesting to note that I noticed the most recent AMD desktop processors would do 64 gigs or 128 gigs for the gamer chips, whereas the server processors would do, I think, like terabyte per socket.
Yeah.
And it's pretty clearly they're going after virtual machines.
No, I
in a
mean,
big
yes,
way.
right. I mean, and it comes down to how many bits of address pins we pin out, right, and how much we support, right. So that's what decides that. So internally, if we only had 32-bit wires for addresses, then you're limited to 4 gig support, right? So internally we have it plumbed to support this big an address range. Now whether it's available or not, we don't know, right? But it's there. If somebody wants to build them, they're free to do it.
Actually, what I was speculating is it looks like the desktop chips are deliberately gimped a bit on their maximum memory allowance.
Part of that is yes, because pins cost money, right? The more pins you want to get out, they cost money. So
given that the upper end of the gamer chips is basically the same socket as the server socket.
Yes, but then you have to also consider that all the motherboard and all the other costs will add up. So if you're looking at whole system cost, it adds up because on the motherboard they have to put down those extra pins, all that other. So it adds up, right? And part of that is it's not a technical decision; it's just a business decision, right? Some of it is just business.
So isn't this more of a case of giving you the customization to get away from general purpose CPU? More in specialized cases now, but you're moving toward that customization where the gamer chip's going to be one set, the low power. I mean, this gives you the whole spectrum, and it's based on what you're going to do with it.
Yeah, I mean, and it's not just number of CPUs or amount of memory addresses. Like there's this general trend to make more and more sort of coprocessors, for lack of a better word, right? So we are making specialized units for specific things, right? Graphics being one of them. We have other special units that can do video encode or decode, right, in the hardware. Same thing for like SSL acceleration or some of these, or encryption, right? Encryption units. So these kinds of things, rather than do them on the general purpose CPU, where they are slower and more power hungry, you can build a custom thing, right? And I think this goes back to that area performance power kind of topic, right? Where we're doing this, like encryption on the CPU is from a power standpoint expensive, right? So if you have a large stream of data that you want to encrypt or decrypt, you're better off offloading that work to a specialized SSL processor, and you basically put your CPUs to sleep. You save power there, and then the SSL unit consumes a fraction of the power that the whole CPU requires. So it's more efficient. But now you have to build that separate unit that you still need the CPU, so your area has gone up, right? But you saved on power. So these are all the different trade-offs that you have to make. Yeah.
Really have a question. Does that AMD also have a roadmap for embedding a PGA on the chip, like Intel?
Not that I know of. Not that I know of.
Just, and this might be a little bit off, but when you're in this you're talking about the fab and the node, and just to back up, and you're down at this level with the mapping, what levels of verification in the mass production unit do you maintain control, random sampling, to verify?
We'll get to that.
Okay.
There's a whole
Yeah.
set. Yeah. And there's checking every step of the way,
Yeah.
right? Because cost of a mistake is massive.
Well, it's mistake also security is
Yes.
something
Yes.
else.
Yes. So anyway, I mean, high level. This is kind of the one page. No, it's a good question, right? But this is kind of the one pager that we come up with and says, okay, these are the high level features, and this is what we think we need in the product, and then we go from there. So then, sort of the next step of the high level design is you break down one of those bigger blocks in the previous picture into more manageable sub blocks. So here's just the CPU core, right? And if you look in the previous diagram, we had 64 of them, right? So you take each one of them, and you break that down into more of the component blocks, right? Like the ALUs and the fetcher, decode, all that stuff, right, in the CPU. So this is just an example for the CPU. And then each of these blocks is what you would basically hand off to a designer and say, go build this one, right? Go design this one. And the architect that is responsible for the CPU would have to understand, okay, I have so many cycles in order to do this. This is my budget. This is how I'm going to partition them, and this level of performance is what I can get, right? So for every big block in the chip, you break it down into smaller blocks that an individual or a small team of people can go and design, right? And it could be that we already have designed this for a different product. We just use it. We don't have to do anything, right? So it depends on what you want to reuse versus design from scratch. So once this level of kind of design is done, you want to now validate that, okay, this design is going to meet my performance, power, area kind of bounding box that we set for this product. So you take this concept and you feed it into a bunch of these simulations that we run. So the first one is a performance simulator. These are typically written in-house. Like every company writes their own simulator. You take some sections of industry benchmarks. You run and you configure the simulator to the hardware that you intend to build. You run these benchmark samples through them, see what it looks like. You guess what your competition is going to have, and see where you stack up. Historically, you would know, okay, these models are off by 5%, 10%, whatever is the error margin, and you kind of account for that, right? And you know, okay, I think we're good. Same with power. There's some, again, so these are very crude, right? So this is very high level. We don't know all the details of the transistors that we're going to implement. But rough guess, are we going to be 20 watts, 30 watts, 50 watts? Where are we going to be, right? And again, this will be over a certain kind of workload, right? And again, that will be different for a server versus desktop versus laptop. Or phone. All these different devices have different characteristics of how much you're used versus idle, right? So another big factor is like what percent of the time are you idle, right? If I'm making presentations all day, my laptop is idle most of the time, right? It's a static screen and nothing is changing, right? So I can basically tell the display controller, keep displaying this thing, and the rest of the chip can go to bed, right? Save power. So these kinds of activity, we call them activity factors, like how active is a block at any given time. So we feed all that into the power estimation model, and then it'll spit out some watt number. And similarly, we say, okay, we've done this high-level design. We want 64 cores. Okay, each core we think will be 3 square millimeters, 4 square millimeters, whatever it is, right? And you can do some scaling. Oh, it was 5 square millimeters in 14 nanometers. Now if I want to go to 10, and we keep the same features, it might be 3. Or we know we're adding some features, so it'll likely be 4, right? So we come up with some crude models for each block, the area, and then we look at how do we optimally place them to form a roughly squarish or slightly rectangular chip, and come up with the overall floor plan and area. So this is kind of the high level thing. And then once you have that sorted out, okay, everything looks good so far, we start the main part of the logical design and verification of that problem. So some of this will happen in parallel. Like, it's not that we can wait for all of that to finish before we start this. Like, there will be other teams that start off and start implementing them, and there's feedback, right? So that's why you have those arrows going every which way. There's always all this feedback that says, okay, this is good, this is not good, this needs to be changed, and we iterate. Logic design. So this is where, like, you now take each of those individual sub-blocks and you start expressing the hardware behavior of what that block is going to be. So you'll have, okay, I'm going to take these set of inputs and I have to come up with these outputs, right? And it could be, let's say for a CPU, you're doing a decoder. So my instruction stream looks like this, and if these bits corresponds to an add or a subtract or whatever, so I'm going to take these bytes coming in, and my output is going to be a set of wires that say whether it's an add or a subtract or what operation, right? That's the level of logic that you have to design. And we typically, so industry-wide, most commercial products are designed using Verilog. VHDL is the other big one that's fairly popular in academia and certain government contracting companies.
Europe as well.
In Europe, again, yes, yeah, that's true. Good point.
How hard is it to translate between the two of them? All right, guess I have questions answered.
It's Verilog is like C, and VHDL is like Pascal.
So it looks like it should be practical.
Yes.
The devil is in the detail.
So I don't know VHDL, so I don't know how much.
It's not really Pascal. The real language is called Ada.
Ada, yeah, Ada. So you could write a transpiler, whatever that's called, but
it's probably, you could do one on a relatively small budget. It's just remember that when you do translation like that, your output tends to be rather larger than your input.
Yes.
Do you use in-house tools, or do you use Cadence or Synopsys?
Yeah, we use third-party tools.
You do?
I mean, there's a few things that we have in-house tools for, but for these days there's very little benefit to doing your own. There are 3 large companies who have become large by buying up every other small company around them. So you have Cadence, you have Synopsys, and you have Mentor. These are the kind of 3 big companies, and so you typically would pay millions of dollars to license tools from them to do all of this. But logic design, VI or Emacs is enough. Yeah. It's just software in a funny language, right? Yeah. I mean, and like software, you don't want to keep writing the same thing over and over again, so you create functions, which we call modules, and you just build a library of them, and then you use things from the library as much as you can, rather than inventing. So things like arrays, FIFOs, muxes. Typically, companies will have centralized teams to create a library of these things, and then every other designer will just go look in the library to see if there's something that meets what they need.
Another question: do you guys use all those like the tools we use as a software engineer, like a source control system and
Oh, absolutely.
analysis?
Absolutely. Yeah. I mean, otherwise, it'll be chaos. So yeah. So I mean, like we used to use Subversion, Clear Case, Perforce. Now a lot of stuff is being done on Git. It's everything. So even a lot of the binary files are version. Because one of the main things you want is reproducibility, right? I need to be able to go and say, if I produced chip X stepping A, I need to know exactly what went into building that chip, right? Because if tomorrow some customer reports some issue, I need to be able to go and find exactly what was there, like correlate the serial number that we shipped to them to the exact, bill of materials that was used to produce that chip, right? And say, okay, this is what they have, and they're saying this problem, which means, this is what I need to investigate. So everything has to be, chain of command, like what do they call it? Like trust, right? Like everything has to be version tagged and everything.
And can I add something? So I think between software design and hardware design, one of the problems we face is there are a lot of IP or like what we say, which are very huge files. Like some of the timing information files is like few gigabytes each, and they're like 25 and which are version by. So you cannot do a Git kind of thing that everybody clones like 100 gigs.
Right.
So there are issues there, but other than that,
yeah, very good point, right? So in some of those cases, we will put them in a common directory, and everybody links to that directory rather than make an individual copy of all of that, right?
So how much human variability is there in the design? Like if you have two chip guys and you ask them to do the same task, how much of this is going to be different and how much of it's going to be the same?
That way it's no different than two different software engineers trying to implement a function, right?
I think variability is smaller, that's what I believe, but
there's more than one way to do anything,
everyone has its own style.
Everybody has their own style, right?
If you examine the compiled netlist, it might be similar, but the initial code.
Right.
But again, when you say C, for example, there are at least 5 different compilers.
Yes.
When you say Verilog, there's probably just Synopsys and Cadence compiler. So we have to be limited to how much they can
support. Right.
If they cannot support, you have a great idea.
There was another question actually. How is the variability of the actual circuit performance, at least LTL level simulation performance varies by the compiler? Did you see
Oh,
yes. Very much different.
Yes, there is difference, right? And it's not just like performance-wise. They're sometimes even functionally slightly different. And there are things like because you're expressing hardware and all of this is parallel. There's very easy to introduce like race conditions, right? And a simulator is somewhat deterministic that way, right? So it will parse that and simulate that a particular way, where some other simulator might do it slightly differently. So, and we have found this in the past, like the easiest way to find race conditions in your design is to just run 2 different simulators. And if you just stick to one simulator, there might be a race condition and you always win that race, right? Whereas somebody else, you might lose. And it's a lot of effort because now you'll be even more limited in what you can do. You have to be limited to the intersection of those 2 vendors, like what they support. But if you're willing to subject yourself to those constraints, it can be, and the extra effort in doing that, you can find issues. We've seen that in the past.
But and also the simulations, you can kind of give you a range of the input like clock skew and stuff, so you can actually.
So yeah, so there's a lot of other things you do to compensate for that, right? So there's like we do things like we'll skew the edges, jitter, like clock edge would not always be at a particular time. You move it 1 picosecond this way, that way. There's things that we do in the design to force more randomness into the thing to mimic what would happen in a real system, right? There's some randomness that will come up because of temperature changes and the humidity. All of these affect the physical chip. So we account for it, and that's why for a lot of other cases we just put margin, right? You want a circuit to run at 2 gigahertz, which means you have 500 picoseconds time between flop to flop, right? You don't want to design to 500 picoseconds. You'll do 460, and that way, okay, something changes this way, that way, you're good, right? Because chip to chip there is variation, right? So you have to account for all of that.
When you change your design, how much does that change the real estate of the silicon?
Depends on what kind of change.
Well, it's two different people design the same function.
Yes, there are stupid ways to implement things, and that would cause chip to be much bigger. But that's where we have reviews of the design, and so if a junior engineer is doing it, there'll be some senior engineer looking at it as like, okay, no, that's fine, it works, but that may not be the most efficient way of implementing it. And in some cases, there might be different ways to express the same hardware in Verilog or VHDL. But then once you go through the synthesis flow, they might end up with the same set of AND gates, OR gates, whatever it is underneath, right? So then you might not see any difference. So it highly varies.
And what's the granularity of reuse? Like if there's a DDR4 controller in one generation of chip,
Yeah.
you don't just you just drop that in, where is the
Pretty much, right? So let's say you're talking about 10 nanometer process from TSMC, right? Let's say, and you've designed a DDR controller that goes for DDR4 controller that works with that process. For every product you make in 10 nanometers at TSMC that has that needs a DDR controller, you'll use the same thing.
So it costs next to nothing in design once you've done the first one.
Yes.
Maybe not next to nothing.
So there is a little difference in the steps, in the sense that if you're talking of supporting different frequencies, then you'll have to change it. So DDR is a bad example because it's locked to what DIMM you put externally. But if you have some other block in the middle, right? Let's say some CPU core. Let's say you take a CPU core and you say, I want to use it for a laptop as well as a desktop, right? Well, desktop I want to run at 4 gigahertz, whereas laptop I only want to run at 2 gigahertz. And so your constraints might be a little different, right? So logically they'll be the same, but physically they'll be different. Anyway, so you kind of go through this whole process. You do your logical design, and then there are some things that are analog in nature, like these high-speed drivers and things like that, where there's all these delays that are analog. Like there's wire delay, right? You go from here to here, there's some delay, and you can't really model that in a pure logical sense, right? And there are other things that are voltage dependent and things like this. That again, because in this thing you're limited to 0 or 1, right? Effectively, there's one more, but I'll skip that for now, right? So basically, all you know is this thing wire high or low, right? That's all you know. But the real world is still analog, and so there's some like models that we build to sort of from a purely simulation standpoint predict model how a certain analog circuit will behave. But that's not something that we can use in the actual silicon. So those will be designed separately and you swap in. You just make sure that logically they behave the same. And then when you do the design, you need to understand what timing you want to go to, right? So if you have a bunch of logic, you'll have to partition it based on what frequency targets you want to hit. So here's a very simple example of Verilog, and it's a 4-input MUX. You have these four inputs, which are each 4 bits wide, and you have a select that selects which one of these what you want to bring out to the output. And this is the Verilog equivalent to it. And as you can see, it sort of looks like C-ish syntax. There's case statement that picks which one. And you'll build something like this. I've hard coded it the width to be 4 bits, but typically you'll parameterize that and make it a parameter, and that way you can do 32 bits, 64 bits, whatever it is. You can, when you instantiate this example, instantiate this module, you can specify what width you want, right? So those are things that you will do in the design. So in this example, there are no clocks involved. If you look at it, there's no clock signal. This is so every time the select toggles, the output will change, right? Whenever the inputs are the select change, your output. And this is kind of what this always block says. Always at star means always at any signal that's underneath that block. Anytime any of those changes, I want you to evaluate this loop, right? So the case statement will be evaluated anytime any of these inputs change. But there's no clock involved. So here's another example, which is where actually things happen on the edge of a clock. So can someone look at this and say what it does? The name kind of gives it away, but
Left shift.
left shift. Here there's also a reset signal. So if reset asserts, then the shift register is set to 0. If not, you take the bottom 3 bits of the previous value, you shift that left, and then you append the new bit that you want to add to that, right? And so the top bit gets thrown away every time. And this less than equal to symbol is actually a different kind of assignment operator that says do it on the next clock edge.
That's a time-deferred assignment,
Yes.
as opposed to a less than
Yes.
or an assignment error.
Yes.
Okay.
So this basically says at the next pass edge, take what you have on the right-hand side.
So in other notations, that would be sreg prime.
Yes. Yes.
Gets
sreg t+1 equals at current sreg this thing, right? So in the next time interval, you get that.
Right.
So
That's sort of referencing a time future version of the symbol is familiar to me from software verification languages, which are pretty much moribund, I guess. But
So the entire chip is like 100 gigabytes of functional definition
stuff like
text.
this. Yes.
So this then gets compiled into something that, how does that turn into transistors?
We'll get to that.
Oh, you get to that.
Yeah.
Okay.
Yeah.
Yeah.
This is mesmerizing.
To a point.
it's turtles all the way down.
To a point, you were commenting of C versus Pascal. The use of begin and end makes it look rather
Yes.
more like Pascal than C.
Correct. But the parenthesis, like the curly brackets, is used for append function. So basically, anything within these squiggly brackets is a concatenate. So they decided to use it for that, and then now you're stuck with begin end or you could do the Python way and then use syntactic white space, which I guess at that time nobody thought of doing that.
Well, it's quite possible to use them for both.
Yes, but yeah. So this is where you actually have a clock and things happen edges of the clock. So one of the interesting things about hardware design is when you're going through all of this, one of the things you have to design up front is what we call DFX, which is designed for test and designed for debug. There's also DFM, which is designed for manufacturing. But these are things that you have to build into the chip, which will almost never be used once a chip is at a customer site, right? So this is all your test harnesses that you have to put into the chip so that once you manufacture the chip, you can test it. But once you've tested it and you know the chip works and you ship it to the customer, this circuitry is useless, right? It's not going to be used in in what we call mission mode, right? When the customer is using it. So some of this, like some of the DFD features, we've exposed to software. So performance counters and some hardware level breakpoints can be used by the end user.
Unless they're selling it to certain highly technically skilled end users who will sometimes solder on wires to your test points and say, oh, this is what it's doing. Hey, we connect these two bits together and suddenly it works, it does its job a whole lot better.
I was going to say that I seem to recall there have been issues with these kinds of debugging features that can be used in nefarious ways. Do you ever how to use fusible systems where you turn it off before it leaves the manufacturing plant?
Yep. So some of these features, like particularly if you can get into secure state within the chip that you don't want exposed. So I'll give you an example. So if you have an HDMI connector on your, if you support HDMI, then and you support HTTP encryption, then you have to get a key from Hollywood to do that encryption, right? Now that key is we purchase from whatever that consortium is, right? And we have to put it on our chip, but we obviously don't want anybody to find out about it. Now, if you expose these hardware debug mechanisms, somebody with the right skill set could conceivably go and try to get at that, and that will get the manufacturer into trouble with Hollywood. So we have to protect those, right? So there are fuses and other things that we program that once we've done with our testing, that access is removed. And when we do our testing, we use dummy keys, right? We don't use actual production keys. There's always some test keys that we run, and then we do all our testing with the test keys. And then once everything's been tested and you want to ship, you burn the real key in, and then you set basically the lock bit that says you're locked out of ever getting it. So even we can't see it, right? So we can't get to it.
Although it's sometimes fun when the engineering software escapes.
So you can get the software, but in this case, you're hardware-wise locked out, right? So unless you get hold of a focused ion beam machine and you know exactly which point to unblow the fuse and do certain things, you can have the software, but the hardware will not grant you access.
So there's a similar technique. Some of the keys actually embedded in the products, you have to apply like crypt hashes and so that someone just dumps the binary and they can find the keys.
Yeah. So all those, so those things are in one-time programmable fuses. So a lot of those things we'll just put them as fuses, and is not software readable physically. And those are some of the challenges from a design verification standpoint. We have to make sure that electrically there is no way to get that out to something that can be read by software. But still, the circuitry that needs it still needs to be able to get to it, right?
So all the design for debug stuff stays physically in the hardware that gets shipped.
Yes.
It's not like in a compiler where there's the debug. And
you
don't
can't
have ifs or anything.
Right.
You can't. You don't strip them out at any
No,
point.
you can't strip the symbols. Like all that is in the chip, right? So that's one of the differences, and that's why I included the slide here, is because you have to build this into the product, because you can't take it out once you have the chip.
Do you know if any of the more paranoid customers have worked with you to verify or accept this? Or?
So
He could tell you, but then it'd have to kill you.
yeah.
Some of these techniques are not evil, meaning that there's one way you chain all the flip-flop, all the registers together, just to inspect if there is a manufacturing fault, if something is stuck at either 0 or 1, right? So that fundamentally is not bad.
Oh, I'm not saying
Yeah.
it's bad. I'm curious in from a security point of view because this is at the bottom of the stack, right?
So, right. So conceivably, you could have a customer
Yeah.
that demands a third-party audit of
Right.
this,
Yeah.
right? And
I understand what you're saying about
yeah,
all the
right. I mean,
verification as you go through
so
and
it's very hard for us to manufacture a chip without these features,
Right.
right? Because then how will we know if this chip works or not, right? Or if it doesn't work, why the hell does it not work, right? That's what you want to find out,
Yeah.
right?
Yeah.
So we have to put these in,
Right.
but you're right that there might be some paranoid customer that absolutely does not want something to leak out, and then what do you do?
Like the DoD, but then you couldn't tell us that, or the NSA that doesn't exist.
I don't know. I don't work with them, so even if I knew,
Yeah, the
which I don't know,
Xbox
but
is-
yeah.
But if you worked for them, we'd have to tell you we didn't work for them anyway.
what fraction of the real estate has to go to this DFT stuff?
That's a good question. I don't know. I mean, there's a certain. I mean, we try to minimize that, obviously, right?
But
Because
is it
it's
1/10%, 1%, 1/100th?
it's probably single-digit percentage.
So
I
it
don't know
actually,
the
it
exact
does
number.
cost something.
It does cost money. Yes.
We're not talking about
Yes.
a 10% effect.
Yes, right. But at the same time, like if your only way to find out if the chip was defective or if you find the defect, how to fix it, right? If that's resulting in you throwing away chips because you don't know how to debug them, then you save money by this 1% that, let's say it's 1%, right? This 1% extra that you spend would save you in terms of yield later on. Otherwise, you just run your battery of tests, you pick the ones that work, and then you just throw away the rest, right? And you don't know why they didn't work. But if you have these features, you go and debug them and say, oh, it doesn't work, and oh, by the way, it doesn't work only when the temperature is like 75 degrees, and this is why, right? Okay, so if I have some application where it doesn't require me to run at 75 Celsius, I can still sell this chip, right? So then you can still have that chip be usable even though it technically failed a certain criteria.
So there is something called an speed test. I will let you say that when you come to that point, but we need to have certain responsibility because when you come to the last step of bidding, then you want it to run fast.
Right.
So you need to have an industry test.
And it's not some corner thing that we can break off before we ship it. It has to be woven through the entire chip, right? And I'll have a slide later on that.
So you do debugging in simulation, and then you actually make the chips, and you test it again.
Yes.
And so if you find a fault there, then you have to make a whole new mask.
Yes. So if it's a bad enough fault, then yes, you have to redesign, make the new mask, and take the cost of materials hit, as well as, more importantly, time to market hit in that, right? But again, there are I'll get to that, but there are not everything is black and white like that, right? There's things you can do. So once you have your logical design sort of started going, in parallel you start this what we call design verification effort, and this is to basically verify that logically your design is doing what it's supposed to do, right? So going back to that decoder example, you're building a decoder, and if I send an instruction that's an add instruction, do I really get an add signal at the other end, right? And does it do it, at every permutation, every combination? If I send an add followed by subtract, does it still come out? If I switch it around, subtract add, does it still come out? So all these different cases that I have to verify to make sure that this particular block is doing everything correctly, right? And it's hard because there's a lot of internal state. So sometimes you will, if you just do subtract, add, it's fine. But then something else happens, set some other bit, and then it stops working, right? So there's a huge. So if you think of this as a state space, it's massive, right? So you have to do a good set of tests to verify that you caught all these cases. And if you, like I said, if you miss anything, it can be very severe, right? So that's why, so the last line is typically you have 3 people doing this for every guy doing the design. So you need 3 smart people to catch dumb mistakes that the other guy made.
How did that balance just sort of evolve empirically?
Kind of, yeah. I think this is across the industry. This is general rule of thumb.
Just in terms of how fast people tend to work and what you
Yeah,
can get.
yeah, and then like simulations, how fast they are, bunch of different things, right? But a lot more work goes into like verification than it is to do the design, right? So just think about it. That state space has to be explored, right? So one guy did the design, but then created all this huge state space that has to be explored. So you need other people, right? And typically, you don't have the same engineer that designed the block writing tests for that block because you'll have the same bias, right?
Yeah, you want it to
So
bias, right?
So you have a spec for this block takes this inputs and produces this output, right? And both the designer and the verification engineer is looking at that spec and doing the work, right? Not really looking into the.
I assume you can't exhaustively test the state space, so you have to intelligently do it, and that's why you need the 3 verifiers.
That's right. So you have to do sort of design of experiments, right, to come up with a minimum set. And we do a bunch of random tests, like so we sequence of instructions. Let's randomize that. Let's randomize the operand. So okay, I'm doing an add. I'll just randomize the 2 inputs and then verify that the output is, the add is correct. So there's a lot of random things you do, and then you think about the particular corner cases. Okay, I'm adding 2 32-bit numbers. What if there's an overflow, right? Is that handled properly? Shift register if everything is empty, or a FIFO, empty, full. All these conditions, you enumerate, right? And you write coverage for them, right?
So typically, what's the balance between using simulation versus formal verification?
So formal, formal is basically you list out the properties of this thing, and then you formally try to prove that this design meets all the properties, right? That you want. In typically. Because of the state space, right? The moment you expand your design, your state space grows exponentially, and these formal tools will just choke and die, right? And I've seen that, right? Just by addition of one additional module, cause the tool to like chew up 256 gigs of RAM and then crash, right? State space is huge, so it's done typically on very small pieces of blocks, right? So for example, like you take the library, because this library is going to be used on multiple designs, multiple places in the same design, you want to make sure that the library elements are absolutely correct, right? So you take each element and say this mux, and you can say describe the properties that if the select is this, then the output has to be this, right? And you can describe out those constraints, and then present it to the formal tool, and the formal tool will verify, yes, this design meets the thing, right? So you do it for very small pieces and critical pieces, right? So like a FIFO, or particularly asynchronous FIFO, where you're reading in one clock domain writing in one clock domain, reading out in another clock domain. There's very easy to have things pile up and you go out of sync, right? So those kinds of things where you say, okay, this is my property. Every time I do a write, I expect to see that value be read out. And if the FIFO fills up, that I can't do a push if it's already full. I can't do a pop if it's already empty, right? So these kind of things you describe as properties, and then you have the formal tool kind of go run its formal proving and prove that these conditions don't happen, right? And we found issues like that where like under some very, very esoteric case, you could have where you're trying to read and write at the same time to the same location, right? Which is non-deterministic, right? So you don't want to do that. So things like that you can find, right, and fix in that design. But the moment you expand, you have to rely on simulation because you can't do that.
Is this something that AI is eventually going to help with?
I've been asked that question several times. I don't know, right? so as it is, right, for formal tools, just specifying the constraint is a huge time, expenditure, right? So and this is where, like, management wants results, and you as a thing, I got to get all these constraints written, right? Whereas somebody else can just start throwing random stimulus at it and say, oh yeah, this is good, right? Whereas the formal process will take a long time, but you 100% know that your design is correct or not correct, right? If the formal tool converges, and you have your answer, right? But simulation, I can run 1,000 tests, I can run 10,000 tests, still not hit some corner condition. I don't know, right? But to
Pure
some
math versus applied math.
right. But for some manager, I say, I wrote 1,000 tests, 998 of them are passing. I'm working on fixing the other 2. And the formal guy, I'm still writing constraints. I realized that, based on the inputs, these 2 things can't happen at the same time, and this tool found that case, right? But that's illegal, so I need to fix the constraint, right? And you try again, and you try again, right? And you have nothing to show for till you're finally done, right?
So you have 737 Max.
So it's hard.
That's a clear case where management overruled engineering and formally doing things. I mean, obviously not in this business, but that's like they go until they don't, right?
Yeah. So I mean, it's you, and it's a question. I mean, it's human tendency, right? You want to see steady progress, right? I wrote 1,000 tests, right? How many did you write last week? I was at 500. Oh, great, you wrote 500 new tests. Where's your formal? Like, I don't know. I'm still debugging these constraints, right? It's hard to be in those meetings.
So with my own intuition, actually, I feel like that the inside the neural network is very good at finding typical patterns, but it's not good at finding inside the corner cases. I mean, so my intuition is that that's
right
the
now,
area that
right now,
the
yeah.
human brain is overpowered at the
No, but for instance, right, like it's not that you're going to go to 0 verification engineers, but if you could go from 3 to 2, for instance, right, you might be able, if you moved your, I mean, I'm just saying that you could imagine as this stuff grows exponentially, that if you could shave 2 months off time to market by having like semi-automatic AI assistance for some of these things, it would really pay for itself. That's
yeah.
I don't mean to overstate the sort of blue sky thinking, right? But you do wonder if you could wipe out the 90% of the tedious things, what would happen? I mean, it's not a well-posed question because I don't understand it. But I'm just going to pretend I'm management. Just make it work. I saw deep learning in Business Insider. Why are we using that? Where are you on this?
Can I add a bit more? So the thing is, finally, the product is a hardware and a software product. It's not just a hardware product. So there will be errors in the hardware, but fortunately, there is a firmware guy writing the software. He'll be able to remove it from the spec or hide it or put a workaround, so the final product still works in some ways.
So not every bug is a showstopper, right? There can be workarounds. Okay, you have this bug, which means you can't use this feature. Okay, is that critical? Without that feature, do I not have a product? Maybe, maybe not, right? Depends, right? If the chip won't come out of reset, well, that's a showstopper, right? You have to fix it, right? Otherwise, you don't have a product, right? Well, if I this weird case where the compiler generates this instruction followed by this, I have a problem. Like, okay, here's a patch to GCC. Don't do that.
Until until the system crackers get in and suddenly you start seeing all your servers slowly turn to slag.
So it's
everything is a balance. Right? I mean, at the end of the day, right, as you point out, it's a balance of a high-dimensional economic, within some economic envelope. And obviously it works because you guys sell lots of chips and your stock is up, right? So,
no, but you're right. This is an enormous level of effort that has to be put in, right? And whatever you can say is.
But and also, can you even find enough people? For instance, are the number of people you can hire that can do the job an actual constraint on the company? For instance, may or may not be. I don't know.
It hasn't been so far, but right now everybody wants to go work on a machine learning job, so it may become a problem. I don't know.
Just give them that. This is why I'm management. I don't know anything, and I can tell you what to do.
But they are working on doing some
still it's too
Since
much.
in the research, right? I don't think any company has put that in sort of their mainstream flow. Yeah, right. Yeah. So for the most part, it's a little bit of formal and then a large amount of simulation, right? That we do it, and so you drive random inputs, but constrained, right, to what input conditions are actually legal in your design, and then you have a whole set of assertions and other checks to make sure that the input and output match what you expect. And then there's like a lot of time is spent on both functional coverage as well as code coverage. And by functional coverage, I mean you could write elaborate patterns that says, okay, I saw this signal toggle, 2 cycles later this thing happened, 3 cycles later this thing happened, because you determine that's an interesting case through the path, right? And so you write all these cover terms, and then you have the standard code coverage. Okay, did I cover this mux and so forth, right? So I won't go through these diagrams, but here's kind of the example. So the DUT stands for design under test. So that's your block that you're trying to verify, and you build these like complex environments to drive stimulus through whatever interface. Which means my command bus has to be 1000 because that's my command encoding for a read. And then it also generates random inputs on the data, for example. And then whatever response you get back, you say, okay, I send a read transaction, I expect to get this data back. And then that kind of goes up this path, the monitor checks it, and then you can have all this stuff reported to a scoreboard that keeps track of, okay, I sent 8 commands, did I get 8 responses? And were those responses in the correct order? And did they have the right values, right? So all this, and that also feeds into the functional coverage. Okay, did I test all these different cases?
So this is a virtual piece of software at the moment.
Yes.
What you're talking about. This is the software simulator.
Correct. Correct. So you build all this in your software simulator. And here's an example from sort of the RISC-V test bench that they built to verify one of these cores, right? So the thing in that gray shaded, that's the actual RISC-V CPU core. And the top box, that's kind of the interesting one, the reference model. That's the sort of a C++ model of how the RISC-V instruction set behaves, which means, what are the instructions, what are the encodings, what are the registers, all that stuff. So you feed random generated assembly code that gets put in the memory, and then you trigger the core to start fetching from that address and start executing those instructions. And there's a monitor that sees, okay, as a result of executing these instructions, what memory address did I change, what registers got changed. You look at all of this, and then you feed the set of inputs into the reference model. The reference model will tell you if you write this, if you execute this instruction, this register bit should change, right? And then that feeds into the scoreboard, and then the monitor will be monitoring, which registers changed as a result of that execution. So so the monitor will tell the scoreboard, and the scoreboard compares. Reference model expects this. The actual device did this. Did that match, right? And if it fails, then you terminate the simulation and you flag it as a failure. And this includes all the other kind of assertions that can be inside the design itself, right? So you have a one-hot encoding for something. So if multiple bits are set, that's an error. So you have all these checks that you put in there. And here's an example of a very simple test bench that I wrote for that 4 input mux. I won't go through details, but here's basically where you're instantiating the DUT, right? This is the device under test, which is the mux 4 that includes all the other kind of, and then here in the initial block, I'm assigning random values to the inputs, and then over there is every clock cycle, I'm incrementing the select just to pick a different select value, and then I'm also changing 2 of the inputs, right, to see what happens. And then I let this run for like basically 10 cycles, and then I'm done, right? So notice there's no checking over here, right? I didn't implement any checking in this test bench, right? But I can run this through the simulator, and the simulator will give me a log file because I put this $monitor statement, which is basically a printf that says every time one of these variables change, log the output, right? Log these things. And so you got a log like this, and somebody can go and say, okay, A, B, C, D is this. Select was 2, which means I expect C, and that's the value I got in the out, right? So somebody could physically manually take a look at this and say, yep, the design is behaving correctly. The other way to look at it is from a waveform view. So this is a sort of a timeline of each signal, and you can put the cursor down at any point, and you can verify that given the inputs for those values was my output correct. So this is obviously very manual, very time-consuming way to do this, which is why you build all that automation that I mentioned in the previous slide, where you have these automated models that understand how this mux should behave, and then automatically checks for any given set of inputs, is my set of outputs correct? Complex designs, right? So if I were to take a typical desktop chip, let's say, that we're trying to simulate, the whole chip, I would be able to get anywhere between 10 to 30 cycles of clocks simulated per second of simulation, right? So think about that, right? So rough. When you manufacture the chip, you get the chip, you power on. In the first second, you have run through more cycles than all simulations put together. Once you're running at 2 gigahertz, you ran 2 billion cycles in 1 second, right? And all the simulations, you would not be able to do that, right? And this is every company the size of AMD, Intel probably has a server farm with hundreds of thousands of servers, right, to run all these simulations in parallel, and it's still very slow, right? So one of the ways to get so there we're talking about tens of hertz. That's how we call it, right? So 30 cycles per second. 30 hertz is your simulation cycles per second, right? 30 hertz. That's pathetically slow. And the only way you can make meaningful, get to all these deep states is by randomizing the initial state, right? Okay, I'm going to put random values in my cache, see what happens, right? Did the design behave correctly? Because by the time I get to getting those values in the cache through normal program execution will be an eternity. I cannot simulate that. So you just randomize your initial state. But then I'm limited in terms of what kind of software I can run, right? I can't run a simulation and try to boot Linux kernel. I can't even run through BIOS, right? Let alone boot an OS kernel, right? Now, if I want my chip to know that I can boot it, one way to do that will be to take all your logic, put it in an FPGA, and if you did your FPGA design properly, you could get a few megahertz of time, right? So it's like multi-orders of magnitude faster than what I can simulate, right? And at that speed, you could attempt to, boot into BIOS, do those kinds of things, right? And it also helps software development, right? So there's some firmware that has to be written or some driver that has to be written. You could conceivably start doing those once you have that FPGA available. There's, in addition to FPGAs, there's also hardware emulators, which are basically massively parallel, special-built processors that take this design and map them into all these individual processors. So instead of one CPU running this whole simulation, you map it into millions of these tiny bit-sliced processors, and then you can get a few kilohertz out of that. But the capacity is more. So I could fit a reasonably sized chip in an emulation platform, whereas an FPGA I'll be really constrained by how much I can do.
So so there's all these trade-offs, like slow, but I can do a ton of them. Then emulation is somewhat fast, but still gives me good capacity. And then FPGA, and it's also visibility. So here, I ran the simulation. I have visibility into every single wire on the chip, right? If I go to emulation, it starts getting expensive, right? I have to limit what debug information I dump out. Once you get to FPGA, it's sort of like a chip. I get very little visibility into it, right? But yeah. Sure. So while your design and verification is happening, the physical design team comes over and says, okay, we got these gates, we got these Verilog statements. How do I translate that into actual transistors? Right? This is the stuff that actually has to get to production. And so basically, between these three bottom boxes is the majority of the team time, effort, everything is spent on this part. All that put together is like very small compared to this. That physical design flow itself has a few different steps, right? So you start from your Verilog RTL at the top, and you feed it through a synthesis tool. It's like a compiler that translates it into gates, right? So by that I mean you take your abstract Verilog representation and you convert it into a set of NAND gates, NOR gates, OR gates, XOR, all these component gates. And the connectivity between them, right? So that's expressed in what we call a gate level netlist. So that's kind of the first step. Next is you have to go through timing, place, and route. And I'll have some more details, but that basically translate these gates into physical placement of transistors on a grid. And then that's the final thing that gets shipped out. So that GDS2 format is the one that gets sent to the foundry, and they make the masks off of that description, and then you get your chip back. Like I said, logical synthesis converts this RTL description into logic gates, and most modern synthesis tools will first minimize the amount of logic, right? So when you write in Verilog, it's sort of meant to be human readable, but it may not be the most efficient in terms of gates. And you might be doing certain operations multiple times, right? So in multiple equations, maybe you're ANDing the same two signals together. So then what the logic minimization step would do is to create one gate and then from there fan out to multiple places where that output is necessary. So things like that it will do. And then once it does all that, it maps it to the library of gate elements that you specify, right? So you have libraries of AND, ORs, NORs, XNORs, like NANDs, all these gates, and you have different versions of them based on whether you want it to be a fast switching transistor or a slow, all these different properties of these different cells, and then it also has to consider the timing target. So I want this circuit to run at 2 gigahertz. That requires certain placement, certain ways of synthesizing this, like picking which elements I want to use, which ones I want to place next to each other, things like that. And then, so the netlist file is really, you can think of it as a textual representation of a schematic, right? So if you have these different gates connected together. So here's the example, right? So it's just 4 single bit things connected, as a mux, right? So based on my select signals and the 4 inputs, I get 1 output, right? And so that mux example is now boiled down into these set of AND gates and NAND gates and inverters in this case, right? So the text representation of this picture is basically what that gate level netlist will be. So the next step is to do the final timing and then place and route. So you take each block here. So you have an AND gate and you have an inverter, right? So now you have the physical layout of what a NAND gate will look like, and an inverter will look like. You place them and then wire them up based on this schematic diagram. And you have to do that with the timing constraint, right? So this whole thing, if it had to be done in a single cycle, then you have to do it a certain way. If it could be over multiple cycles, then you have to put flops in between. So all these things get looked at by this timing tool. And then the wires are routed. And this is where you have to provide some constraints, right? You have to say, let's say I have a 64-bit bus, and I want all these 64-bit buses to travel the exact way, right? Because I'm timing critical. I don't want there to be sharp bands such that one is shorter and one is longer. Maybe that causes a skew in the bit between the first, leftmost bit and the rightmost bit, right? So you have to specify these constraints, because if the receiver circuit is sensitive to that time difference, then you don't want there to be any difference, right? And so you want them to be, you specify all these constraints. I want these routed together, or these have to be short because I want to minimize the latency. These ones are kind of, these debug signals. They can take their sweet time. It doesn't matter. I can connect them in a circuitous way, whichever I find most optimal. The other thing is the clock tree generation. So it's called a clock spine, and so you have a clock feeding all these different blocks, right? And you don't want there to be a big skew. So if you have one just linear wire driving the clock, and then you tap at it from different points, what will happen is that the clock edge at the beginning of this chain will be slightly early than the clock edge at the end of this chain, just because of that propagation delay. And you only can tolerate certain skew between different blocks, right? So you have all these constraints that have to be fed in, and then the clock circuit topology will be determined based on that constraints that you provide. So it ends up looking like a star pattern rather than a linear pattern. So you radially go out so that and again, there's different ways to do this, and the tools will have to take care of that. But there's a lot of engineer investment to be done to tell the tool to do the right thing. And then, once all
this is like you're basically saying, right? Like I'm an MBT, I want this bus to go to this station or whatever, and then like the software just lays out the city.
Yes.
And it works.
Yes. It's a lot of effort because
I guess how much of this is like you push the button and it's like generate New York?
Yeah.
Does Boston, or does it end up looking like Boston?
Because if you're not careful, it will end up looking like Boston, and then you'll get lost, right? And you'll never get anywhere on time, right? And then somebody will have to say, like, hang on, this rotary right over here, this is a killer. Like, I can't have this rotary over here, right? Or I can't have this like six-way intersection.
So just in practice, how much of this is like you just push the button and say go, and then it's hard to imagine like how this all works.
So
the geography of it, right? Because it's basically a 3D geography, right? How many layers are in these things?
So several. Like metal layers are 11, 12.
Right. So it's
this is where the engineer comes into the picture, and that engineer has to provide the right set of constraints to say this is a problem or this is not a problem. And then it's iterative, right? You provide some set of constraints, see what the tool comes up with, and says, oh, no, that doesn't work, right? I need to add this constraint, or this is maybe too constrained. I can remove this constraint and still meet my target, right? And this is that iterative process that I talked about, where you have to go through this whole thing several times before you get a design that's meeting several criteria, right? So if sometimes the tool will fail, right? You say, I want this whole thing to fit in 0.1 square millimeters, right? The tool does everything it tries to fit in this and says, oh, sorry, I can't do it, right? Now you have to go look and say, oh, did I what constraint can I relax, right? Maybe this 0.1 square millimeters is not negotiable, but I can say, oh, this doesn't have to be very high performance. So for this, these logic cells, I don't have to pick the fat transistors that can drive a high current or switch faster. I can pick a small or slower transistor. So I can sub in a different library element that's slower, right? But it's smaller, so now it fits. things like this, right? It's been 20 years since I've done this, so the technology is like, I might be talking out of my behind here, like I don't know. But that's generally my understanding of how this iterative process works.
How do you test that it actually created a design that will work?
There's steps. There are steps. There are several steps for that. I'll show you.
Okay.
So here's sort of a very simple example of a 2-input NAND gate, right? So Verilog representation, very simple. Not of A and B. Here's the schematic, like the symbol in the truth table for that. Here's the transistor representation. You have in CMOS, right? So those are 2 PMOS and 2 NMOS, transistors, and that's the output. And once you get to masks layout, it looks like this, right? And this is one library element that gets generated. And again, how fast this will switch is all dependent on width of some of these things. So I can make a bigger, fatter thing that'll switch faster, but then it occupies more space, right? So I can have a library which has a few different variants of this based on what I need for that circuit. And so that 4-input mux turns into this. I have not actually gone through it to make sure that it's actually what it is. I just kind of copied it from here.
When did this actually start working, sort of in history, right? Because obviously, the 8088 wasn't designed this way.
Yeah. So back in the day, all this stuff was done. So they call it mask because it was done in a room 30 by 30, and you laid down tape, right? So it was called a tape out. Because,
yeah, that's right.
Because you sent these tapes, right? You literally taped stuff on the floor, right? And so every company would have this room that was, I've told 30 by 30. I've never seen one, and then they would stretch this huge sheets of paper and then lay down tape for each of these different layers of masks, right? But there were only 2 layers of metal back then, and it's not as complex.
This is like basically a half micron process.
Yeah,
micron process.
Even bigger, right? So if you look at the Intel 4004, for example, right? You could make out every transistor from the die shot, right? And people reverse engineered things that way. Like, good luck trying to do that without an electron microscope.
Even half an electron.
It's very hard.
Can't see.
Yeah.
It's not a 3D confocal X-ray thing.
Yeah.
You can't see layer 5 in an electron microscope, right?
Yeah.
There is, let me just say this, when I was in graduate school, first, actually, I manually drew
right.
this.
So after that, right. So that's a progression, right?
Yes.
People went from laying tapes on paper to then drawing them by hand, like in a CAD package, right? Like similar to your AutoCAD, something like that, right? So your 3D modeling type thing. So you drew this by hand, right? And humans were far more efficient at doing this, given the algorithms of the day. And then I think sometime in the early 2000s is where these tools became good enough that most non-critical portions of the design could be done push button like this, place and run.
And now,
and then like certain critical data paths where you're short on timing, the engineers will still manually do this and create a more efficient layout from that perspective. Now I would say the majority is done this way.
By majority, are we talking
90 plus percent, right? And then there will be like some very custom, very critical blocks that will be hand done, right? And so I mean, just in the 20 years that I've been in the industry, I have seen. So there used to be people whose job description was mask layout design.
I mean, I was looking at this.
And the number has gone down drastically in the past 20 years.
But then, also there's like, everything has like 90-degree angles, right? Like you wonder that if in some point somebody relaxes that and says, okay, if we go to arbitrary, like if that becomes a parameter, I mean, but the design space, of course, is enormous, right?
Yep.
But you do but at a certain point, right, if you do that, it could save 10% of the layout of the chip. It would pay for itself, right?
Yeah. but if some human did it, yeah, sure. But now you have to hire an army of people.
No,
to
no,
do
I
this,
mean, the
right?
only way it happens is if you take away, call it the 90-degree angular constraint
Yeah.
in this design and let the machine figure it out, right?
But-
Because it has the functional, I don't know, this is just,
Well, squiggly lines are very difficult because when you do the mask, right? So remember, all this stuff is you have to etch a mask
yeah, it's
output, right?
photolithographic.
Right? Yeah. So the lithography like works on straight lines too, right?
Yeah, no, I'm not talking about, but I'm saying that you have 90-degree intersections. If you had 45 or 30, like if you quantize that, I mean, I'm just saying
Yeah,
that at a
yeah.
certain point, the full 3D simulate, like that will go and be a full 3D finite element quantum simulation, right? At some point.
Could be. Yeah.
At some
Yeah.
point. No, I mean, if
Yeah,
computational power.
You're the physicist. I don't know.
I'm saying that if you have exponentially increasing computation at a certain point,
Yeah.
it will be cheaper
Yeah.
because of the real estate and the reliability
Possibly.
to do so,
Possibly.
right? Anyway, I don't know, they
Yeah.
can go on, but.
So, one quick thing, just since I'm in the industry, maybe when you say 10 nanometer process, can you tell on that figure
Oh.
which is the 10 nanometer?
Yeah. So this width would typically be 20 nanometers, two times the minimum size. Right?
So no, there is the MOSFET width is there, right?
Yeah. So
See, the red lines are the gates,
yep.
and when they pass through the green lines,
So-
so the width
so
of that
this-
red line is
yeah.
like what you call is 10 nanometer.
Yeah. So this much, right? So this is the actual transistor. This part here, right? And that's
Yeah, it's in
that's-
red because if it were blue, it would be Intel, and they're not at 10 nanometers, right? That's how you can read the diagram. The red part's right there.
purely coincidental. Right. But
Yeah, well, you
but
have
that's-
some homage to green. It was at 14 nanometers.
But that's the yeah, good point. That's the feature size you're talking about.
This particular picture shows what, about 5 different layers?
So no, it's actually only two. Metal layers are only two. This purple and the blue. So these, I don't know what this peach colored thing, that's polysilicon. That goes in the gate. And then these hatch sections are actual the substrate. So the PMOS or NMOS doping of the substrate, right? So every feature that you see here goes into some level of mask, right? So you have the substrate mask, and then you have the metal, the poly mask, the metal 1 mask, metal 2 mask, right? And now we're up to metal 11, metal 12 masks, right? So higher level routing would be on upper and upper levels, right? And then wherever the two layers intersect, that's a via. So this is very similar to a PCB layout, right? Where you have multi-layer PCBs. It's the same idea.
Now, if you tried to go diagonally, you probably have more than the 2 layers. That's not-
Yeah. So the more, so typically we follow the grid because then it's hard to.
No, there's registration and all kinds of.
Yeah,
I mean, it's-
yeah.
You have to.
And then the other thing is like now you have metals at 2 different layers, right? Separated by a dielectric. That's a capacitor. Right? So now you have to account for all of that. And if you have these things going at weird angles, I don't know how you calculate.
No, like I said, until you're at the point where it's a finite full 3D quantum simulation,
Yeah.
you can't do it.
Yeah.
But again, exponential computation.
As it is,
power.
like so simulating this, right? Using SPICE simulation is like several orders of magnitude slower than the Verilog simulation that we talked about, right? So you better invent your quantum computer to be able to do this. Right?
You can simulate your quantum computer because run real slow.
So one more fact, maybe in that every metal has a thickness, and when it's talking of 2 layers, it's probably okay. When you go to 12 layers, the different thicknesses for different levels
Correct.
of metal.
Correct.
And
Yeah.
the whole electrical properties are the same, but the calculation is different.
Yeah, that's what I'm
Right.
saying. That,
So that's-
that
that's
it has
all-
to be a full 3D
Right.
finite element quantum simulation, right? That's
So
it.
because all of this you're talking about capacitance,
but you get all
have
that if you literally solve the
inductance,
Schrödinger equation.
and then there's like all these other things like okay now with each of these things was behaving like an antenna. Now you have to talk about RF, right? So you can have resonance, right? We have to design circuits separately, specifically so that there is no resonance at 2.4 gigahertz or 900 megahertz, any of these commonly used cell phone bands, right? Because I'm running on Wi-Fi, and if I cause a resonance, I'm going to end up with a pile of sand again, right? So it's insanely complicated, right? And you know, I've been doing this for 20 years, and it's a miracle all this stuff works, right? I mean, the chip has.
I'm not getting on an airplane anytime soon. But it's just powered by AMD. I'm like, all right.
You know,
maybe that train's looking pretty good.
Like, each chip has billions of these, right? Like this is a transistor. There's billions of these transistors, right? You know. And this is the full layout of a MOS 6502, right? From Apple II and you know bunch of those old times. So you know you could still see individual features, right? I did not get permission to get layout from one of our current designs. You will, I mean, at this scale, this is the whole chip, right? If I put the whole chip, you will not see anything. You will just see this sea of metal, right? Because you will not see any of the underlying things.
You may see some areas that sort of like some gridded areas where like you've got caches that look like a grid.
Yeah.
Or
So actually, I had one thing for sure.
You could just wave your laptop. We know it's AMD.
This is an actual chip, and you can, if you look at the thing, you can sort of see some of the features, right? That's a quad-core CPU, so you can see if you can make out the 4 cores in that.
All you really need is glasses that are built in an electron microscope.
How many gates were in the 6502?
18,000, something like
Yeah. It kind of looks like a rug.
that. Yeah.
I took apart one of my microwave ovens once, and it was a 65.
Really? Yeah.
I can run Unix on mine.
Well, the thing is that what was the 6502 doing in the microwave?
It's cheap that you can put it anywhere.
Probably
the clock.
Yeah.
Probably the clock and pulse code modulation
For the button. Yeah.
Sorry, which chip is this?
This one?
Yeah. Sorry.
That one? That's a
The tray game.
that's an Opteron. It's a quad-core Opteron server chip.
From what vintage year?
2012.
Oh.
Pretty old.
No, because like, you tell me Opteron, like I had an Athlon in 2001,
Yeah,
right? Like, it
no,
doesn't
this
tell me
is
anything.
this is from 2012, something like that. I don't remember the
I
exact
think
year.
it was 2008 or 9 when you had Optrons. After that, they kind of.
We still made them. Unfortunately, not many people bought them. But
Well, you really need a side-by-side comparison from the AMD chip to a Frito-Lay chip.
So talking about the progression, how people used to design, the master designers, and right nowadays we write very low, we compile it, we have all the tools. You're gonna take a guess and comment on high-level synthesis or the next generation, let's say, design methodology. Do you see that coming anytime soon?
I mean, there's a lot of some things happen within larger companies, and they come up with new tools internally, and then other things like new startups like form, right? And then eventually they get gobbled up by one of these larger guys. I don't know, like it's hard to tell. I mean, at least on the physical design side, like I said, I haven't done it for 20 years, so I kind of don't know what's the latest and greatest. Most of my time I've spent sort of the upper blocks, so high-level design, verification, performance architecture, things like that.
I see.
So I haven't done some of this since my very first job.
Sure. Languages like Chisel.
Right.
Or I'm not talking about C++, but GDX.
Yeah.
Something in between Chisel. Do you see something like that coming anytime soon? Soonish?
So I mean, the advantage of there have been other languages like this, right? Like so digital had its own language, which basically was built for very fast simulation, but then they had their own tools to basically generate something that looked like Verilog, right? And there have been other attempts like this, like there was Blue Spac and things like this, or Chisel is what the RISC-V people use. So I mean, so far I haven't seen anything on a mass scale supplant Verilog or VHDL, right? There's even been talk about, oh well, what can we use like something like Python, right? To do this, right? And it just all comes down to whether the industry starts supporting those things. At the moment, there is like a Python or Ruby-based DSL for domain-specific language for hardware, and Synopsys supports it. Then maybe more people will start using it, right? It's hard to get the industry going, and some of these guys. I mean, it's when was it? Like only this year they started supporting Red Hat 7, right? RHEL 7. We were on 6.2 or till like a few months ago, right? It's an enormous burden for all these things to move, right? So I'm not holding my breath on that.
Sure, thanks.
So once you do the tool runs the thing, now you have to do all the verification. And I think you were asking about this earlier.
Mm-hmm.
How do you make sure that all this stuff matches, right? So first thing is you run targeted timing simulations on that both on the net list as well as on the final layout, and you make sure that timing wise everything is correct.
I doubt your cell phone camera is going to get you a good enough picture to actually resolve any features.
I think that's a 32 nanometer product, if I remember.
Yeah.
Either 32, probably 32, maybe 28.
Cell phone isn't going to get much of it.
But I think if you look at it at the right angle, you can try to make the 4 cores. And then there are all these different checks to make sure that, because all the simulation and functional correctness has been checked using the Verilog, right, the RTL. Now, what if you messed up in any of these steps, right? All these equivalence checks to check that the net list that was produced is logically equivalent to the Verilog.
And this can be bugs in all the tools. Like, how much does that affect things? I mean, yes, I know you can't blame the compiler. Like, blame the compiler is rule number 1 of the first CS course. But
So I mean, that's why I think there's always some level of manual simulation to do the check, right?
Because we're talking about like corner cases or like things like race conditions,
things like that, right?
It's possible. Like I don't like there could be not like a trivial coding bug, but like a design that doesn't anticipate a set of circuits like race conditions or something. Right? It's almost impossible to
things like that have happened. I don't know if it's been major. This, in your experience, is not a significant problem. No, I mean, I have personally found bugs, right, where something didn't simulate properly. It's whether that translates into actual design issues, I don't know, right? It might be just a glitch, just takes care of itself. There's so much.
I mean, the dimension of the parameter space of this is just. I mean, as a physicist, it's just.
It's huge. It's huge space, right? And so yes, there are probably bugs, but this is why I think
it's a question of whether they're significant or not.
Because and that's one of the reasons why these guys are so slow to move, because now they have to run their own library of tests to make sure that with every point release of their tool, they didn't break something, right? They have their own, and every time we found issues, they've asked for snippets of whatever, isolate that problem and give it to them so that they can add it to their test suite, right? So there's a lot of knowledge that's embodied in those test suites themselves, right? Same for us, right? We have like several thousand x86 compliance tests. And each of those tests was written because there might have been some bug back in the day.
Divide by something.
Something, right? Like divide by 0, whatever, right? All these cases.
So if they're concerned about how changing the operating system will change whether or not this tool will work correctly, how When do you decide you're allowed to upgrade to the newest CPU in order to run their tools on it?
So it is a very slow progression. Yes, yes. There's a lot of qualification that has to be done. We have to take every design, run it on the old, run it on the new, and not just one or two things, like a lot of things. And so the thing is, like, we don't change tool sets mid-program.
During a design process.
No. So you, on day one, you decide what, and that's what you're going to go with, right? For the entire duration, right? And so even when those machines get retired, right? You know, okay, now all these projects have moved on to Red Hat 7. You know, like even like for our own tools, the GCC version that we use is controlled. Like we just can't, you know, apt-get or you know, yum install whatever we want, right? You can't do that, right?
Just wait for the little green thing.
Yeah,
on the button
yeah.
and, take
Nope,
the compiler
nope,
suite.
not happening, not happening.
So where's that chip that you're passing around?
It's here.
And how big is the total team, say, for the Xbox or the whatever processor, all
So
in?
it's hard to say because the development is broken down into so many sub-teams, right? For example, there's a graphics design team, right? And they will design those unit level blocks, right? For the latest Radeon card as well as for the APU. So it's very hard to put a number like that. It's in about 1,000 or so.
So you don't, there's no, like, you don't really know everybody.
No way.
Nobody knows.
Nobody knows.
Except as
I'm sure some accounting is happening.
I was gonna say HR or something.
Yeah, no, not even HR. Some like finance guy probably knows because on the budget, every manager has to account.
Yeah.
Oh, such person is working on this project.
But the point being, there's no single human that can actually conceive of all the things.
We're past that point several
that 20
decades
years
ago.
ago.
Yeah, several decades ago.
So like, just to give you an example, 20 years ago, I was at a startup which was doing network processors, and we had about 50 electrical chip designers and about 50 processors.
So it's 200 times bigger than that.
I mean, but the chip complexity, you have to look at that, right?
It's a simple chip.
Right.
It's just interesting to get a sense of, like, as a human endeavor, say, in history. These are, like, pretty much the most sophisticated things that we as a species build.
I don't know if I'll go that far, but it's, but yes, it is pretty. I mean, it is pretty complicated. Right? Sorry. Probably more complicated, but the number of different pieces that have to come together, a number of things. I mean, this is you know, okay. I still haven't finished my entire presentation. There's still more stuff, right? More people to be involved, right? But you know, so here's all the checks that we do. Like against every stage is compared to the previous one. Make sure that logically they are the same, right? And functionally, timing wise, everything is the same, right?
How much more do you have?
It's a few more. I'll rush through. Yeah. And then once you've gone through all of this, is when you tape out, right? And like I said before, tape out was physically you sent those tapes over to make the mask. Then it became tape out, as in you took your whole database, put it on a tape reel, and FedEx the tape reel, like physical, you know, like magnetic tape. And now it's a secure FTP. You send this whole massive file.
The latency sucks, but the bandwidth is excellent.
Yes.
Directly to the Chinese servers for them to not be able to
For an Intel or AMD design, I would halfway expect it to be person with briefcase and armed guards.
So this, you know, this is all, there's like highly secure ways of doing this now. So I don't know the details. I've never been involved in one. So somebody out there has a red button they push and this thing goes out.
And
right?
the entire world.
Right. And then there is like, I'm sure there's like 100 levels of SHA 256 checks and everything to make sure that what we sent is what they got and all that. And then, yeah, then there's a celebration. This is just the first step. Like, okay, you've done your design. Let me quickly go through these steps. So in parallel, there's a bunch of software side development that has to happen, whatever firmware, microcode that has to be done, firmware, BIOS, compilers, drivers, operating system patches, whatever you need to do to get this thing. All this stuff happens, and this is where, like you said, some of the stuff you do in FPGA or emulators because it's slow. And then you also work on pattern generation for testing, and I'll go through that example. So you ship it. People in white bunny suits then take over, and you start with the silicon.
Weren't the white bunny suits expired about like 15 years ago or so?
No, these are all like whatever. I don't know what class clean rooms there are. These are like the highest level clean rooms.
I thought like something like 15 years ago or so, somewhere in there, it became basically completely robotic.
No, there's still people in there. It is. I mean, let me put it this way: there are fewer people in bunny suits, but there are still people in bunny suits.
Because the machines do not work with 100% reliability. That's the problem,
so,
right?
So I mean, no. Plus, there are steps there that so you have to go calibrate some of these things. It's like a car assembly line, right? Okay, most of the stuff is being done by robots, but you still have people watching the robots and doing some things by hand.
I love watching a robot do my job.
So what comes out is this thing. So this is what a finished wafer looks like, and you can see the chip features in that.
How
in that
big
picture.
are the wafers they're doing nowadays?
So it's 300 millimeters wide, so 12 inches, and there is a movement towards going to 450 millimeters. So it was 200 not that long ago, and then it became 300, and now there's.
And the cost savings really are worth it.
At 450, I think it's not there yet. I think that's why nobody big has migrated.
Wasn't like 300 like again 10 or 15 years ago? So it's
Yeah. So it's been that's why we stuck on that. It hasn't moved since then. Yeah. Right. So for a long time it was 200 millimeter wafers, and then became 300, and then 450 is supposedly the next step. So once you get those wafers, you have to run your tests, right? So the next slide shows some of the testing procedure, but basically you know which die are good, which are bad. You mark those. You cut them, and then the cut piece is what I passed around. So once you know which ones are good, which ones are bad, you cut the wafer and you throw away the bad ones, right? The one I have is one of the ones that we were planning to throw away.
What's the typical yield on that? 99% of the
highly guarded secret.
And I guess it's a time-dependent thing too, right?
Yes.
Like
so if it's a new process at the very beginning, right? This is your first kind of run through a new process. It'll be.
The yield is good when the price comes down.
Yeah. So it'll be like it could even be as low single digits yield, and then progressively you get into as close to 100 as possible, right? For a mature process, very mature design.
99 plus
not
percent.
Not 99, but in
90%.
In the 90s, yeah. But then, so you take that wafer, that cut die, and then you put it in the package, right? Which is what you get with all the pins or ball grade, whatever you have, and that's the thing that goes along with it.
And even then, you still get some that are shipped out to customers and turn out to be bad.
This obviously we try to minimize that.
Yes.
But
yes.
Occasionally, yes, mistakes might happen.
Yes, I have.
Or some things might get damaged in transit, like shipment. Don't know. But the testing is done in what we call ATE machines, like automated test equipment, and you put the chip, and then you send generated pattern of input. So all the pins on the chip, you send known patterns of input, and you look at the output, and you compare with what in your simulation you did, right? So there's pattern generation that, like I mentioned before, you do before you tape out the chip. And so you have this library of input versus output patterns. And then the ATE tester will drive all those known set of inputs, compares the outputs, and it does this under very controlled circumstances. Temperature, pressure, humidity, all the stuff is very, very well controlled.
And you're using the design features you put in for testing.
Correct. Correct. Yeah.
And all those steps are performed, all those tests performed for every single chip.
Every single chip. Every single chip. It's not like a a lace chip assembly line where somebody says, yeah, that batch looks okay, or case one, yeah, I'll sample one, yep, salt level is okay, this whole batch is good, right? Every single one has to be tested. Right?
How long does that take, or how much time? You basically you must have like a finite amount of time to run as many tests as you can, right?
So one of the goals is to minimize that test time, right?
So
what is the minimum level of patterns that we have to run to get the most coverage, right, or all known defects, right? And you prove, and that changes over time, right? As you find additional problems. Oh, we found some defects. So certain chips have this defect. Now I need to find that defect.
So how much time typically do you get?
I have no idea. I have no idea.
It depends on the chip, right?
It depends on the chip and the complexity, but
And the cost, really, right?
So
Like
and the thing is, like, depends like how many of these machines you want to build in parallel, right? Because if you want to pump out 1 million chips a month, then you need that level of equipment.
Yeah, so it's all economics,
right?
More than
Yeah.
I see.
So there's like system level testing where you actually put it on a mock motherboard, you boot your OS and do all that, right? So there's different levels. There's born-in testing. You want to run for very long to make sure that there's no defects that come up after some amount of time. So all these tests have to be done before we pack it, before we ship it, right?
Doing a test is a little bit different than burn it. The burn in, you want to run it for a certain amount of time, see if it lasts.
Yes. So
Is that done for every chip?
That's done for every chip. Yes.
Yep.
Yes. I mean, what if a defect comes after, like, if you run it, pushed it for certain hours, right? So there's
But you
some.
don't run the chips that, do you?
The time varies, but what we do is we simulate long-term use by making it stressful and running it for a short period of time, right?
Of course, then there's the problem that it has been suggested that hard drives work quite well at higher temperatures because the burn-in testing uses them at higher temperatures, and therefore they work better at those temperatures.
Yep. So anyway, in the interest of time, let me quickly go through these. Power and performance characterization. So there's every chip that comes out will have slightly different silicon characteristics in terms of leakage, for example. So you might have a chip that's on the power performance spectrum slightly different, so you have to calibrate all of these, right? So there are fast parts or slow parts. So all these corner cases. Within that die, not everything is uniform, right? And so how the doping works, everything is, there might be slight variation, but when you're talking about 6 billion transistors, even a small variation impacts quite a bit, right? So one of the things is, ideal transistor draws no current if it's not switching. Ideal case, right? No transistor is ideal. And as you go to smaller and smaller geometries, it starts to get worse, right? So there's leakage, that we call leakage when a transistor is burning power even though it's not switching. So different parts, depending on the doping and all of this, can have different levels of leakage. So you have to characterize all of that. What is the range of these things that we see? And then there's all these parameters that we have to optimize to get the optimum frequency performance for that.
Are you talking about process optimization or?
No, so there are all these heuristics that so some of it is performance. Like if we consistently we consistently see the leakage is much higher than we expect, then something is wrong with the manufacturing, and then we have to go back to the fab and say, hey, all these parts are leaking like crazy, and then they might tweak something to improve that. But even if it's within the allowed range, within the worst part and the best part, there could be a variance.
I'm confused. Are you talking about bidding the parts here, or you actually change something in each chip?
No, so we try to optimize for like that spread, right? So you see this leakage levels from here to here. Okay, so within this range, what's the best optimal point? So that I'm kind of shooting for that middle and not for the edges, right?
Okay, but this is done sort of after chips are manufactured, but it's not done for every chip.
No,
that ships
so this
to the
is done what we call during initial bring up
Got it.
and validation,
Okay.
right? So you do all this characterization,
Yeah.
then you find the optimal set of parameters, and then you roll that out for the rest of the project, right? And then you have to. So there's always some correlation that we do. So our model, we predicted this level of power. We're seeing this, and so now I have to adjust my heuristics. If I want to stay within this power envelope, this is what I have to do, right? So we do that. Then there's a whole bunch of compliance testing, right? Okay, do we adhere to PCIe standard or USB, DRAM, ISA? If I'm doing my own RISC-V design, then I need to be compliant with what the RISC-V Foundation says. In order for you to call your chip RISC-V, you have to pass these tests. So I have to run through those tests, right? And like literally, we do plug fest, or we plug every kind of USB device you can find. Okay, does our chip handle that, right? And then
I would say of those designs mentioned, it sounds like MIPS is just about dead at this point.
They open source. I mean, they're now in quotes open as well. You don't have to pay a royalty to implement their thing.
I haven't heard of anything MIPS in about the past.
There's still designs out there. Like some of them haven't paid the money to call themselves MIPS, but if you use any MIPS compiler, it'll work.
Wasn't there a patent issue for certain instructions?
Yes. So
Yeah.
MIPS, yeah.
I ran into that with a device.
And yeah, so they would intentionally omit certain instructions that were impacted by those patents, and then you just have your own compiler to not use those, right? So there's all that testing, and then when you find a problem, right? Okay, this chip doesn't work under this and this circumstance. Like, okay, how do you debug it? Right? How do you root cause the issue? So in the simulation, we could look at all the internal signals, but here we are sort of limited to the IOs. Plus whatever other this debug features that we put into the chip, right? So this is where all that DFD work that we did before pays off, right? So you can use oscilloscopes or logic analyzers to look at the external outputs, and then you have these DFD features to allow breakpoints. Then you have this thing called scan, which lets you look at internal flop state within the chip. And I have a slide that shows next one. And you have these performance counters that can help identify any performance bottlenecks, right? So you count how many cache misses you have, for example. And that way you can optimize your software to minimize cache misses and you fit in your cache. So here's an example of a JTAG scan. Each device can be anything. It can be the whole chip or modules within a chip, and the similar picture looks even for flop to flop in a chain. So you can send a signal and then scan the value out. And so you can look at those outputs on the TDO pin that comes out. And so all these devices would have a regular clock, but they also have this test clock called TCK. So when you're doing test mode, you mux the TCK in instead of the regular clock. And these TCKs are typically a slower clock. And then you can get to examine some of the logic within each device. And you can send particular commands through the port. And you can say, okay, read me all the values of this chain of flops, right? And then it will get it out. It's somewhat slow, but at least you can get some visibility into the internal state. And like you were saying, if any of those flops has a manufacturing defect where it's stuck at low or stuck at high, you'll see that coming out in your scan.
Do EPIC chips have this? Can you JTAG an x86 fast processor?
Not once it's shipped.
Oh, okay.
So this is what you're talking about. Then there's a physical process that severs, like burns little holes.
Correct.
Essentially burns small holes.
These are fuses, right?
Yeah, whatever.
Right.
Or something.
Right.
But there's a physical.
Yeah,
there's no,
physical connection that's not.
And you're literally air gapping in a way.
In a way.
That part of the hardware.
Yes.
Very possibly something like what's known as an E-fuse, which.
Yes. Yeah.
No, but it's an irreversible physical process. That's
Correct.
That's
Correct.
the point, right?
Yes.
Hopefully irreversible physical process. Sometimes heat or other effects might.
Well, yeah, I mean, you can, like I said, you can go in through a focused ion beam and try, right? If you know the exact place where that transistor is and you want to try something,
No,
you
but
might
also,
right?
also the FI, depends on how big the FIB beam is. If you like, you could actually being a physicist, if you can.
Yeah, no,
It's possible that you could set up something, right? That because your process is only 10 nanometers and your pitch is tens of nanometers, the FIB is not necessarily going to be able to converge on
Absolutely,
that.
absolutely.
Well,
There's a lot of collateral damage, right? So the question is, for the thing that you're interested in, is that collateral damage acceptable, right? So it's not a slam dunk. So once you go through all that initial validation process, you know, okay, this chip is good. I've worked out manufacturing, you know, most of the major manufacturing defects that were causing me yield problems, and then all the all the other optimization is all done. This looks good. Let's start volume manufacturing. So initial samples, you would manufacture a few thousand, something like that, and you run it through your testing and qualification, and then you go tell the fabs, okay, I want to start volume production. And then that's when you have to give them some estimate of, okay, how many do I need? How many do I need this month, next quarter, you know, all these kind of targets for what your sales things are. You have to get those commitments from the fab upfront. So there's this whole, what AMD calls wafer supply agreement. So you have to sign all these things and say, okay, I promise to buy X number of wafers from you. So you do all that. And so once you start getting volume chips back, now you have to do your high volume automated testing. And as I said, you have to test every single chip. You say your product works under a certain temperature range, then you better make sure that it works in those ranges. And then you have to sort and bin these parts based on what passed and what failed. So an example is, you know, you run every chip to be at the highest frequency that you want to sell. Like, okay, I'm targeting a 4 gigahertz processor, so I want to test every chip at 4 gigahertz. Then, well, some of them will fail. But wait a minute, they pass at 3.8. Okay, this is not my top bin, but this is my next bin. And I sell, you know, this one is $100 and this one is at $80, right? And so you get that. And some of them just don't work at all. Those go things, you know, in the trash bin. Yeah, you throw it in the trash, right?
Should we recycle the silicon?
I don't know what they do.
12 layers, so you have all the metal, and like it's not cost effective to recycle that.
I don't know. I think you just incinerate them. I don't know what they do. That's a very good question. I have no idea what we do. Hopefully it's not a big number. So if your yields are, you know, fairly high, you don't have a bunch of these rejects.
I believe they will recycle because the purity of the silicon is so like refined in the ingot which they use. They will probably use that.
But you already doped it, right? So
yeah, but it would be easier to clean that rather than.
I see. Okay.
Oh yeah,
okay.
yeah, no.
Maybe you polish that and then get rid. Could be. I don't know.
When you go to a larger wafer, does that decrease the yield?
No, it just makes it harder from a manufacturing standpoint to guarantee uniformity across the whole die. Right. So the smaller your die, the fewer chips in there, and so there's less variance, right, from one chip to another. The advantage of going to larger dies is that you have fewer things at the edges. So as you have a circular die, and your chips are all square or rectangular, right? And so there's stuff at the edge that's going to be discarded. So the larger your wafer, the less of that discard area you can fit more chips in that thing. But the difficulty is guaranteeing uniformity across how many ever chips there are in that size.
I mean, it certainly would be that the unused parts of the wafer get recycled.
I don't think so.
Right?
I mean, they still get doped. So it'd be the same as a bad chip, right? Those corner pieces. Anyway, so once you've gone through all this, tested everything.
Someone's next generation factory starts cutting it into chips first and then doing all of the other processes.
So you don't
That
want to do
seems unlikely.
No, I mean-
that's the equivalent of doing it on a 1-inch wafer.
Yeah, yes.
You never
So,
do that.
so all these things, right? They work on circular things, right? Like what you know. So why don't we have rectangular pipes? It's very hard, right? To do all the fittings and everything. So the only place where they use rectangular pipes in nuclear subs, because space is a constraint. If you have square pipes, you can put more together. Because if you have circular pipes, then cylindrical pipes, then you have gaps in between, and that's area, right? So it's a lot of it is physical constraints on how the equipment
You also
manufactured.
don't have uniform flow profiles the same way in square pipes. I mean, there's.
Correct.
I don't know if
Correct.
there's only.
Correct. You're right.
I'm
You're
sorry
right.
to be the gadfly physicist.
You're right.
talking it.
Anyway, so this is the last slide.
Yeah.
Yeah. So once you've tested everything, you take the parts that you know works, you put them in boxes for retail, or if you want to go into, like, if you're shipping to somebody like HP or Dell who has this big volume manufacturing line, so you put them in trays, and they have robotic, pick and place machines that will place them on the motherboard and so on. And that's it.
I didn't
Thank
know
you.
that they had rectangular pipes on nuclear submarines.
Yes.
So, into Ron.
This is great.